Yes, students, let us start with our assignment of chapter 2 function. The question says express the following functions at a set of ordered pairs and determine their range. We have to determine the range and we have to write the function in terms of the ordered pairs. As we know, the function is like a machine which will take some input which is known as x, and after applying some rule over x, we will get the values of output which are known as y. Here, the first function f of x is, okay, the rule is f of x is equals to x square plus 1. The values of x can be taken from the set A, which are minus 1, 0, 2, and 4. So we can keep minus 1, 0, 2, and 4 instead of x. If I write minus 1, then instead of x, wherever I am having x in my rule, I will substitute the value which is minus 1. So minus 1 square plus 1 will give me answer 2. Similarly, f of 0 will give me the answer 0 square plus 1, which is equals to 1. F of 2 can be written as 2 square plus 1, which is equals to 5. Similarly, f of 4 will be, instead of x, I will substitute 4. So 4 square plus 1, which is equals to 17. So these values 2, 1, 5, and 17 are the respective values of our y. So now we can write the given function in terms of ordered pair, and that is f is equals to minus 1 is paired with 2, because when x is minus 2, value of y, that is f of x, is 2. Similarly, y is paired with 1, 0 is paired with 1, 2 is paired with 5, and 4 is paired with 17. So this will become my final function in terms of ordered pair. As we know, the range is nothing but the list of all second elements. So 2, 1, 5, and 17 will become my range. So range of function f would be 2, 1, 5, and 17. It is not necessary to write in any order. We can write in any order, 5, 1, 2, 17 also. Now coming back to the second question, which is g. G of x is equals to, given it is 2x. X can be taken from set A, which has all the natural numbers which are less than equals to 10. So here x can take the values from 1 to 10. And the new rule applied is f of x is equals to 2x. G of x is equals to here 2x. So x can take all the values from 1 to 3 up to 10. Obviously, the answer of y will be double that of x. So when we substitute 1, we'll get the answer 2. When we substitute 2, we'll get the answer 4. And so on up to the last value would be 20. So here also, we need not write all the different values of x and y, because we have at least 10 different values of x. So we'll directly write, okay, g of x is equals to 2x for x belongs to A. F of x will become either 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. So the pairing can be written as G is equals to 1 is paired with 2, 2 is paired with 4, 3 is paired with 6, 4 is paired with 8, and so on up to the last pair would be 10, 20. Obviously, the range would be list of all the second elements. So here also we can say the range of g of x will be equals to 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. So this completes our first question. We need to find just the range and write the function in the ordered pair. Now we'll go to the second question. Next, our third question. A is equals to -2, -1, 0, 1 and 2. Function f is from A to Z. F of x is given x square minus 2x minus 3. First, we have to find the range of f of a. Again, here we can treat this as a normal function with a given rule, which is x square minus 2x minus 3. We'll write the values of x from one side. X can take all the values from -2, -1, 0, 1 and 2. Then we have to find the values of y. So we'll substitute values of x in the function to find the range. First, we'll find f of -2. F of -2 means instead of x, wherever we have x in our equation, we'll write just -2. So substituting -2 over here, we'll get -2 square, that is 4. 4 plus 4, 8. 8 minus 3 will be 5. So when x is -2, value of y comes is 5. Then again, we'll keep substituting different values of x. F of -1 will be -1 square -2 into -1 minus 3. Wherever we have x, we'll substitute the value of x, that is -1 in second case. Sure. So this will become 1 minus minus plus 2 minus 3. 3 minus 3 will become 0. Then f of 0, 0 square minus 2 into 0 minus 3 will give us the value equals to -3. F of 1 will give us the value 1 square minus 2 into 1 minus 3. So 1 minus 2 minus 3 will give us the value -4. Then f of 2, which will be equals to 2 square minus 2 times of 2 minus 3. It is 4 minus 4 minus 3 will get the value -3. So the different values of y which we are getting is 5, 0, -3, -4. Obviously -3 is again repeated. We will write it once only. So 5, 0, -3 and -4 are the values of y. So we can say the range of this function r of f will be equals to -4, -3, 0 and 5. Next, we have to find the pre-images. Pre-images for 6, -3 and 5. So here pre-image means the value of x and 6, -3 and 5 are the values of y. From the range, we can say y never takes the value equals to 6. So for 6, I can directly write for y equals to 6 is not possible because it is not in the range. So its pre-image does not exist. Now for y equals to -3, the value of x which we are getting is for -3, the value of x is 2 and 0. So for x, y equals to -3, the value of x is 0 and 2. The pre-image of -3 will be 0 and 2. Next, we get the value of 5. We get the value y equals to 5 when x is equals to -2. So we can say the pre-image of 5 should be equals to -2. X plus 1 by x. Now we have to prove f of x whole cube is equals to f of x cube plus 3 times of f of 1 by x. So basically we are given one function which has some rule related to x, which is x plus 1 upon x. The LHS now says f of x whole cube. So we can say it is nothing but x plus 1 upon x whole cube. Here we'll use one identity of a plus b whole cube, which says a plus b whole cube is a cube plus b cube plus 3ab into a plus b. So here also we can use this identity. Instead of a we have x, and instead of b we have 1 by x. So we'll use this identity over here, and we'll get the value which is equals to a cube, so that is here x cube plus 1 upon x cube, which will be my b cube. Next is plus 3ab, so that is 3 times of x into 1 by x. Inside the bracket, we'll have x plus 1 by x. Let us keep this as our equation number 1. Now we move to the RHS. In RHS, we have two different terms, f of x cube and then 3 times of f of 1 by x. First, we'll find f of x cube. So f of x cube. Here, instead of this x, we have a new term, and that is x cube. So wherever we'll find x in our rule, we'll substitute x cube instead of x. So the first term is x. Instead of that, I will write x cube, because now the place of x is taken by x cube. Initially, we had x inside the bracket. Now we are having x cube inside the bracket. So wherever we'll find x, we'll write x cube. Okay, x cube plus 1 upon, again we found x, so we'll write x cube. Now, next, the second term given over here is 3 times of f of 1 by x. So now what happens is, wherever we'll find x, instead of that, now I will write 1 by x. Instead of x, I will write 1 by x. So here, the first term is x. Instead of that, I should write 1 by x, which is given inside the bracket. Then plus 1 upon, again, instead of x, I will write 1 by x. This will be now equals to, obviously, 1 by x would be as it is, plus denominator of denominator will become the numerator, and we'll get x. And obviously we have 3 times, so we'll write 3 outside as it is. Now adding the second equation and the third equation, we'll get f of x cube plus 3 times of f of 1 by x will be equals to x cube plus 1 by x cube plus 3 times, inside the bracket I'll have x plus 1 by x. Let this be equation 4. Obviously we can say equation 1 and 4. All the terms are equal. LHS is equals to RHS. So we have proved this. Okay. Let us move now to the next. Now let us see the next question. Write the following relations as a set of ordered pairs and find which of them are functions. So the ordered pair in the first part, sub-question A, the ordered pair x and y is such that y is equals to 3x. What should be the value of x? X should be equals to 1, 2, and 3. And y, of course, belongs to 3, 6, 9, and 12. So I will start making the ordered pairs. So in the first relation, we can say if x is equals to 1, obviously y, which is 3 times of x, will take the value 3. When x is equals to 2, y is 3 times of x, so it will take the value 6. Then similarly, when x is equals to 3, y will be 3 times of x, which will take the value 9. X has only 3 values, 1, 2, and 3, so we won't write any more ordered pairs. Okay, now we have to check whether this relation is a function or not. So obviously, the condition to check whether the relation is function or not is the domain must be utilized and the element of the domain must not be repeated. Here the domain is 1, 2, 3, which is given in the question, and here we can also see 1, 2, and 3. All the elements of domain are utilized. So our first condition is satisfied. Now looking to the second condition, which says the element of the domain must not be repeated. So here we can say 1, 2, and 3. In all the order pairs, we have different values of domain. So our second condition is also satisfied. So yes, we can say the first relation is a function. Now we'll check for the second sub-question. In second sub-question, it is given the ordered pair x and y is such that y is greater than x plus 1. Now what we should take instead of x? So we can take the values of x as 1 and 2. And value of y should be from 2, 4, and 6. Okay. So first again we'll form a relation where my first element will be the value of x, which is 1 and 2. The condition here given is y must be greater than x plus 1. The values of y are 2, 4, and 6. So when the x is 1, x plus 1 would become, when x is equals to 1, x plus 1 would become 2. So I should write the values of y which are greater than 2. From the available values, I can say 4 and 6 are greater than 2. So I will write 1 can be paired with 4 and 1 can be paired with 6 because it satisfies our given condition. Now when x is equals to 2, x plus 1 will be equals to 3. Now I should find the value of x, I should find the value of y which is greater than 3. From the available values, we can say again 4 and 6 satisfies our condition, they are greater than 3. So again 2 can be paired with 4 and 2 can also be paired with 6. So 1, 1, 4, 2, 4, 1, 6, 2, 6 is my required order pair. Here we can see that the first element 2 is repeated and even 1 is repeated. Because the second condition here is not satisfied, we can say the second part or the second relation is not a function. It violates the second condition. Now we'll look for the third sub-question, which says order pair xy. The condition here is x plus y is equals to 3. X and y both belongs to 0, 1, 2, and 3. Okay, now we'll form a relation in which we'll write the ordered pairs which will satisfy this condition, which says value of summation of x and y must be equals to 3. So if I write x is equals to 0, the value of y must be equals to 3, and 3 is also inside this available value, so I'll write 0, 3. Then if I write x is equals to 1 here, the value of y should be 2. So I will write 1 can be paired with 2. Obviously 2 is also inside the given values. If I write x is equals to 2, then the value of y would become 1. So we can say 2 comma 1 is my next order pair. If I write the value of x to be 3, then the value of y comes to be 0. So obviously I can write 3 comma 0 also. All the values of the x have been utilized, so we can now complete the relation. Now we'll check for the conditions for this relation to be a function. The first condition says domain must be utilized. Domain here is 0, 1, 2, 3. As you can see, 0, 1, 2, and 3. All the values of the domain are utilized. So it satisfies our first condition. Now for the second condition, all the elements of the domain must be unique. It cannot be repeated. Here we can see the first element is never repeated. Every time we have the unique values of first element. So second condition is satisfied. So the third relation is a function. First and third are function, second is not. Next question, here again we can see f of x is equals to x cube minus 1 upon x cube, and we have to show that, we have to prove f of x plus f of 1 by x is equals to 0. Okay, now we'll start with f of x. So f of x is directly given over here, which is nothing but equals to x cube minus 1 upon x cube. Okay. Also, I need to find f of 1 by x. So now to find f of 1 by x, what I can do is, instead of this x, I'll write 1 by x. So here we have x cube. Instead of that, I'll write 1 by x cube minus 1 upon, again instead of x, I will write 1 by x cube. So the first term would become 1 by x cube. The second term would become 1 upon 1 by x cube. The denominator of denominator will become the numerator, and finally we can say this is nothing but 1 by x cube minus x cube. Let the first rule equation 1 and the second answer be equation 2. Adding both 1 and 2, we can say f of x plus f of 1 by x is nothing but equals to x cube minus 1 by x cube plus 1 by x cube minus x cube. Obviously, we can see over here x cube minus x cube gets nullified. 1 by x cube minus 1 by x cube gets nullified. So the final answer that we get is 0, which is what we have to prove. Okay. The question here is, let f and g be two real functions defined by f of x here is 1 upon x plus 4 and g of x is equals to f of x plus 4 whole cube. We have to find f plus g. We have to find different operations on the function. There is f plus g, f minus g, f into g, f by g, 2f, 1 by f, and 1 by g. Okay, we'll first start with the first part, that is f plus g. So basically we are given two functions. F of x is nothing but 1 upon x plus 4 and g of x is nothing but x plus 4 whole cube. Okay. Our first subpart, f plus g, definition say f plus g is nothing but f of x plus g of x. So directly I will substitute the values. F of x is 1 upon x plus 4 and g of x is x plus 4 whole cube. No need to simplify. We can leave it all over here. This can be taken as our final answer. If we are, in any case, if we simplify, then the value will be x plus 4 whole raised to 4 plus 1 upon x plus 4. Okay, but that step would be redundant. That is not needed because just we need to use the definitions. The second subpart is f minus g. According to our definition, again, we can say this is nothing but f of x minus g of x. Again, we just need to substitute the values of f of x and g of x and subtract the terms. So we can write this as 1 upon x plus 4 minus x plus 4 whole cube. Okay, we'll leave it all over here. The third part says f into g. Again, definition says this means the functions have to be multiplied. So first I'll write the value of f of x, which is 1 upon x plus 4 multiplied by g of x, which says x plus 4 whole cube. Now here, the power of x plus 4 in numerator is 3, while the power of x plus 4 in denominator is 1. So we'll simplify over here and we can write the final power of x plus 4 will become 3 and the final power should become 2 and the final value will be x plus 4 whole square. The fourth sub question says we have to find value of f by g. Again, by definition, this is nothing but f of x upon g of x. First write the values of f of x, which is 1 upon x plus 4 divided by value of g of x, which is x plus 4 whole cube. Since we are dividing, this denominator will go with x plus 4. Denominator of the numerator will become the denominator and the final value will become 1 upon x plus 4 whole raised to 4. Now let us move to the next sub question, fifth one, which is says 2 times of f. So this is 2 times of f of x, which is equals to 2 times of 1 upon x plus 4. So that is 2 upon x plus 4. The next sub question says 1 upon f. 1 by f is just finding the reciprocal of the function. So it would be 1 upon f of x, which is equals to 1 upon x plus 4. Again, the denominator of the denominator would become numerator and our answer should be x plus 4. Similarly, we can also find 1 by g, which is reciprocal of g of x. That would be 1 upon x plus 4 whole cube. That completes our. Let us now see the second question. Set A is equals to PQRS. Set B is equals to 1, 2, 3. We have to check which of the following relations from set A to set B is not a function. Condition for any relation to be a function would be, first condition is all the elements of the domain must be utilized. The second condition says all elements of domain cannot be repeated. It cannot be repeated. So the first element should not be repeated in the ordered pairs. Now let us apply these two conditions to our first options. Relation R1 is P1, Q2, R1 and S2. First condition, the domain is PQRS and here also PQRS is utilized. So it satisfies the first condition. Looking for the second condition, obviously in each and every ordered pair, the first element is unique. So first element is not repeated, second condition is satisfied. So this one is a function. Looking for the second option, relation R2 is equals to P1, Q1, R1 and S1. Again, PQRS are the list of first element. all the elements of the domain PQRS are utilized. It satisfies our first condition. For second condition, obviously first element is not repeated over here. So second option is also a function. Now checking for the third, P1, Q2, P2, S3. Here we can say the first element used are P, Q and S. Here R is not utilized, so it violates our first condition. It also violates the second condition because the first element P is repeated. So it violates both the conditions. The third option would not be a function. Looking for the fourth option, P2, Q3, R2 and S2. Here we can easily say P, Q, R, S, all the elements of domain are utilized and each and every ordered pair first element is different. Second condition is also satisfied. This is a function. So which of the following is not a function? Option C would be my answer. Relation 3 is not a function. Here f of x is equals to 3 into x raised to 4 minus 5x square plus 9. We have to find f of x minus 1. Okay, so f of x is given. It is equals to 3 times x raised to 4 minus 5 times of x square plus 9. Now instead of x, we have to find the value of f of x minus 1. So wherever we have x, we will substitute now x minus 1. So 3 into x raised to 4, instead of that I will write 3 into x minus 1 raised to 4. Then minus 5 times of x square, instead of that I will write x minus 1 whole square. Plus 9 would remain as it is. We can expand this, but currently we are not interested in finding the final value or simplifying the function. So we can write this as our answer. Let's see our next question. If f is a real function defined by f of x, which is x minus 1 upon x plus 1, then we have to prove f of 2x is equals to 3 times of f of x plus 1 upon f of x plus 3. It's a very interesting and IMP question. Here f of x is given. It is equals to x minus 1 upon x plus 1. Now we have to prove in the LHS we have f of 2x. So everywhere in our f of x, instead of x, I will substitute 2x. Rest all terms would remain as it is. Now in our RHS, it is given 3 times of f of x plus 1 upon f of x plus 3. So first 3 would remain as it is. I will substitute the value of f of x, which is x minus 1 upon x plus 1 plus 1, of course, upon f of x. Again, I will substitute x minus 1 upon x plus 1 plus 3. Now taking the LCM, we can say this is 3 times of x minus 1 plus x plus 1 upon, in denominator also we can take the LCM, which will become x minus 1 plus 3 times of x plus 1. We can expand the bracket and we can write this as 3x minus 3 plus x plus 1 upon x minus 1 plus 3x plus 3. 3x plus x becomes 4x, minus 3 plus 2 becomes minus 2. X plus 3x in the denominator will become 4x. Minus 1 plus 3 will become plus 2. Obviously, we can take 2 common from numerator and denominator, and the new value will become 2x minus 1 upon 2x plus 1. 2 gets cancelled out. Our final value is 2x minus 1 upon 2x plus 1, which is same as the value of our LHS. So RHS and LHS is equal. So we have proved our given relation. Again, a very important question. We have to find the domain of each following real valued functions of the real variable. For the domain, we have already studied. Okay, we just need to look for the restrictions which are only applied when we have either root or we have 1 upon something. So we have something in the denominator, a term with respect to x in the denominator, or term related to x in the root. If it is inside the root, then we'll say the term inside the root must be greater than equals to 0. And if we have something in the denominator, we will say the denominator must not be equals to 0. So we'll look for these two restrictions. Otherwise, the domain of the function would remain R. Looking for the first question, here f of x is equals to 1 upon x. Since we're getting the second condition over here, we can directly say x cannot be equals to 0 and x takes all other values. So domain of this function f would be all real numbers except 0. Now looking for our second, here f of x is equals to 1 upon x minus 7. Here also, since we have something in the denominator, we can say this denominator x minus 7 should not be equal to 0. Obviously, which means x cannot be equal to 7. So we can say the domain in second case would be all real numbers except 7. Looking for our third function, which says f of x is equals to 3 times of x minus 2 upon x plus 1. Again, we won't look to the numerator because we can apply any value of x in the numerator. We have just the restrictions over denominator. So we'll say the denominator must not be equals to 0. So x plus 1 cannot be equals to 0. Obviously, this means x cannot take the value equals to minus 1. So domain of this function now would become all real numbers except minus 1. Fourth function is f of x is equals to 2 times of x plus 1 upon x square minus 9. Here again the denominator should not be equals to 0, so we can say this term x square minus 9 should not be equals to 0. X square will not be equals to 9 when x is not equals to 3 or minus 3. So x cannot take the value equals to 3 and minus 3. So we can say domain of this function will be r minus 3 comma 3. All real values except minus 3 and 3 can be taken as the values of x. Now similarly applying the similar conditions. In the fifth question, here f of x is equals to x square plus 2x plus 1 in the numerator and x square minus 8x plus 12 inside the denominator. Here we can create a factors in the denominator. Again, we will write numerator as it is. We won't disturb the numerator. We'll write x square plus 2x plus 1 as it is. We are just interested in denominator, which should not be equals to 0. So this factors of the denominator can be x minus 6 into x minus 2. So this factors should not be equals to 0. We can say x should not be equals to either 6 or 2. So we can say the domain of this function would become all real numbers except 2 and 6. So this is how we'll find the denominator of any rational functions. We'll look for the denominator and we'll let the denominator not equals to 0. Then we'll find the values which x cannot take, and then the domain will be all the real numbers except the next question. Here involves again finding the domain of each of the real valued functions of a real variable. Here root is involved. So again, let us write the conditions to find the domain. If it involves root, then we can say anything inside the root must be greater than equals to 0. If it involves the denominator, then we can say anything inside the denominator cannot be equals to 0. Let us take our first function, which is f of x is equals to under root of x minus 2. So here we have something. Here we have something inside the root. So we can say here the value inside the root x minus 2 must be greater than equals to 0, which says obviously x must be greater than equals to 2. So from here we can say the domain of this function should be starting from 2 to infinity. Since 2 is included, we'll write the box bracket. With infinity, there is always a open bracket. So the domain of the function will be 2 to infinity. Looking for our second function, here we have f of x is equals to 1 upon under root of x square minus 1. Here we have root and reciprocal both. So we'll satisfy both the condition. First condition is x square minus 1 should be greater than equals to 0, which means x square is greater than equals to 1, which means value of square would be greater than equals to 1 when x will take the values either greater than equals to 1 or less than equals to minus 1. If the value of x is less than minus 1, its square would be more than 1. Again, if the value of x is greater than equals to 1, its square would be more than equals to 1. Now we'll satisfy the second condition, which says x square minus 1 cannot be equals to 0, which means x square cannot be equals to 1, which means x cannot take the values minus 1 and 1. Satisfying these two conditions simultaneously, we can remove the equals to sign and we can say the domain of this function would be from 1 to infinity, since again 1 would not be included. So 1 to infinity union minus infinity to minus 1. Again, minus 1 won't be included. So whenever we have both kinds of restrictions, root and denominator, will satisfy both the conditions simultaneously and then write the respected domain. Now let us check our third function. F of x is equals to under root of 9 minus x square. So here 9 minus x square must not be equals to, so 9 minus x square must be greater than equals to 0. We just have one condition and that is that of root. So 9 minus x square must be greater than equals to 0, which says 9 must be greater than equals to x square, which says x square must be less than equals to 9. So square of any real number should be less than equals to 9. It only happens when x is between minus 3 to plus 3. All the real numbers between minus 3 to plus 3 will have their square less than equals to 9. So the domain, we can say directly, we can write this as minus 3 to plus 3, both obviously included. Looking for our next function, f of x, fourth one, which says f of x is equals to under root of x minus 2 upon x, sorry, 3 minus x. Again, root and denominator both are involved over here. Will satisfy both the conditions. First, we can say 3 minus x should be greater than equals to 0. We can say x minus 2 should be greater than equals to 0. Numerator also has a root. 3 minus x should be greater than equals to 0. So we can say x is greater than equals to 2 and x is less than equals to 3. Obviously, taking x to minus x was RHS. In the second inequality, we can say x is less than equals to 3. X is greater than equals to 2 and less than equals to 3. Further, satisfying our second condition of denominator, we can say we have 3 minus x in the denominator. It should not be equals to 0. So we can say x should not be equals to 3. Now, satisfying all these three conditions simultaneously, it should be on a number line. We can say it should be greater than 3. It should be less than equals to 3, but it should not be equals to 3. So the final value should be including 2 and excluding 3. So the domain of this function should be 2 to. Let us see the first sub questions, which is f plus g. Obviously, by definition, f plus g means adding both the functions individually. That is f of x plus g of x. F of x here is under root of x plus 1 plus g of x here is under root of 9 minus x square. So we'll just write root x plus 1 plus root 9 minus x square. Now for the second sub question, it is g minus f. By definition, it would be g of x minus f of x. So first we'll write g of x, which is root of 9 minus x square minus under root of x plus 1. Next, third is f into g. F into g means we need to multiply individually f of x and g of x. So f of x is root of x plus 1 multiplied by g of x is root of 9 minus x square. We'll keep it as it is. We can simplify this function x plus 1 into 9 minus x square, but we are currently not interested in simplifying and finding the final answer. We just need to apply the definition. The fourth sub question says f by g. F by g means we need to divide f of x and g of x. F of x is under root of, again, x plus 1. Inside the denominator, we will write g of x, which is the root of 9 minus x square. This becomes my f by g. Next is g by f. So that is dividing g of x and f of x. So in the numerator now we'll write g of x, which is root of 9 minus x square upon under root of x plus 1. Okay. Now we'll look for next sixth sub question is 2 times of f minus root 5 into g. So this means we have to find 2 times of f of x, so which is 2 times of value of x, f of x, which is under root of x plus 1, minus second term is root 5 into g of x. So we'll write root 5 as it is, and then inside the bracket I'll write g of x, which is under root of 9 minus square. We want to further simplify the function. Now in the seventh part, it is written we have to find f square plus 7f. F square means f of x whole square. So first we'll write under root x plus 1, which is the value of f of x. Then we'll do square of that. So root and square get nullified. Plus 7 times of f of x, which is under root of x plus 1. So finally we can say the value comes out to be root and square gets nullified, and it will be just x plus 1, which will be my first term, plus 7 times of under root x plus 1 will be as it is. We cannot further simplify, so we'll keep it as it is. Now 5 by g, next sub question, which is 5 by g, which is 5 upon g of x. So in the denominator, we need to write the value of g of x, which is under root of 9 minus x square. What is our final answer? The next sub question is irrelevant. It is printed by mistake. So these are the different operations and the functions that we have done in this question.